In these next couple of videos, we're going to look at ways to find the roots of an equation. We're going to look at the bisection method in this one. The next one we'll look at another one called Newton's method. And in the third video, we'll look at the tools that are integrated in Excel and MATLAB to be able to find the roots of an equation. So we're talking here about a single equation, a single independent variable. We'll call it x. And of course, if x only appears linearly, that is to the first power, that's a linear equation. If it appears in powers of positive integers, for example, we have x squared, x cubed, etc., then it's a polynomial. But anything else becomes a general nonlinear equation. Now, thinking about how we solve these equations, well, the linear ones are pretty trivial. Again, if we're just talking about a single equation with a single unknown. A lot of polynomials can be solved analytically. You've solved quadratic equations before. And when they get to be higher order, unless they're specialized, then usually you're going to have a numerical solution for that. And unless your nonlinear equation is very simple, that's probably going to require a numerical solution as well. So there are two really widely used solution algorithms, the bisection method and the Newton's method. And again, we'll look at bisection in this video, Newton's method in the second, and then Excel and MATLAB tools in the third video. So here's how the bisection method works. We start out with an interval. Those are our high and low guesses of what our variable is going to be that solves this equation. And then we keep cutting that interval in half until we get it down to small enough to say, hey, our variable that satisfies the equation is within this interval, and the interval is small enough for us. We'll see this in an example. It's a little harder to explain in words. So it's important to start out with, though, to realize that if our initial guesses, the function that's evaluated at those initial guesses have to have opposite signs, that makes sure that the method is going to converge to a solution. And so let's take a look at a very simple function. This is a linear function, but again, we can illustrate the method very easily. 7x minus 6, we're trying to find at what value is that equal to 0. And of course, the answer would be 6/7. So we'll show how we're going to get that with the bisection method. Now, we start out by saying we're going to let x vary between minus 10 and 10. And so if I evaluate the function at those upper and lower limits, I'll see, okay, yeah, one's negative, one's positive. So somewhere in between, there is a value of x that satisfies this equation, and we're going to find it by having this minus 10 to 10 interval, having it again, etc. So again, we know that somewhere there is a solution between x equals 10 and x equals minus 10. Now, let's look at what happens in the middle of that. If we put in value of 0, which is in the middle of minus 10 and 10, f of x is equal to minus 6. Now, let's take a look at the graph here. So here's our interval from minus 10 to 10. You can see we've got a positive value here, a negative value here, and in the middle we also have a negative value. So because these two values are negative, but this one's negative and this one's positive, we know that this is the half that we want to keep, that the solution has got to cross between here and here. So again, we keep the half of the interval where the function at the midpoint is opposite sign of the function at the end point. And in this case, it means we're going to keep the upper half of the interval. So now this becomes our new interval, and so we'll evaluate it upper and lower and in the middle as well. And you can see when we do that, we're going to have a positive number here and a negative number here. So in this next iteration, we're going to keep this half, 0 to 5. And again, there's our values. The lower and the mid have opposite signs, so I'm keeping the lower half of the interval, 0 to 5. Now, each step along the way, we're going to say, is this interval small enough? And we're going to compare that once we've decided what an allowable error is, we're going to multiply that by 2, because when we establish an interval that's small enough, we're going to say the midpoint of that is going to be our solution. And we keep doing that until we get to that value. So we'll say our allowable error is half of a thousandth, or 1/10,000th. If the interval is greater than 1/1000th, then we keep going. Once it becomes less than 1/1000th, then we take the midpoint of the range for our answer. Therefore, the precision is plus or minus half of that interval. So here's how we do it in Excel. We'll put in the upper and lower guesses. We'll look at the difference between those two, which of course is 20, and say, well, is that small enough? Well, obviously it's not at the beginning. We evaluate the function at its lower and its middle values. And if those signs are the same, then that means your product, when you multiply the two together, is positive. So we're going to eliminate the lower half of the interval. For the next iteration, you bring down the upper and lower limits based on what you found in the previous interval and use if statements there to say whether that product is positive or negative. Again, look at the difference and say, are we narrow enough to stop? And of course the answer is still no here. Evaluate the function again. Now in this case, the signs are different, which means we get a negative product, which means we'll eliminate the upper half of the interval in the next iteration, and we'll keep going. So we just copy those cells down, and eventually you'll see that the interval gets very, very small. It took 16 iterations to get here, but to 3 significant digits, the answer is 0.857. Now, of course, we know that the exact answer is 6/7. If I want this to be more precise, then we set our allowable to a smaller, our allowable error to a smaller increment. And if we do that, we would increase the number of iterations, in this case from 16 to 22. And even if we set those initial guesses way off, minus 10,000 and 10,000, we still get down to 5 decimal places within 32 iterations. So the bisection method, one advantage of it over some other methods is that if we start out with endpoints that are opposite signs, we know we're going to get an answer. Now, let's look at one more example here. Let's look at a polynomial. And in this case, we want to have an allowed error of 0.0001. And what we do first is just write this as a function that's equal to 0 when the equation is satisfied. So there's our function. And you can see we've just put that into the same spreadsheet. The only difference would be the calculations of the function at the low and mid points. And you can see in this case where I've used a limit of minus 10 and 0, we've converged to an answer of minus 2. But if I change the limits to 0 and 10, you can see I get an answer here. If I go a little further than that, the answer is exactly 4. And if we look at the graph of that function, you can see that if I made the interval minus 10 to 0, then the root I found is x equals minus 2. On the other hand, if I set my intervals from 0 to 10, then I'm going to find the root of 4. But in both those cases, notice positive value here, negative here. We know it crosses somewhere within that interval. Same thing here. Positive, negative, so we know it crosses somewhat. If I, for this particular example, if I'd used minus 10 to 10 as my interval, it's not going to work because you have a positive value here and a positive value here. So when you select your interval, it is important to know that you're going to have opposite signs on those two endpoints. And for that reason, and we'll talk about this as we go along, it's often a good idea to graph your function, and that'll get you close to where the roots are, and then you can narrow in to a more exact value using one of these methods.